here we go. Okay, welcome everyone. Today we start our week 6 and we continue the themes of last week, talking about stellar activity and structure, stellar structure and processes happening within stars, trying to understand more mathematically and more deeply what makes a star and what determines the shape, the form, the internal mechanisms of a star. Like we said, what makes a star tick, or rather radiate. So short recap. Last week we showed this diagram, this schematic of a star in various different forms. We saw how it looks like on the outside in some optical band. We mentioned something on the inside, talking about this equilibrium, hydrostatic equilibrium between pressure, which comes from the temperature, the very hot internals of the star coming themselves from nuclear burning. This temperature heats the gas pushes outside the outermost, or the more outer layers of the star, while gravity, on the other hand, pushes the star inwards. So gravity pulls layers in, pressure pushes them out. When there's equilibrium, the star can maintain a static or hydrostatic shape, and this can go on for a very, very long time. As we said, billions of years on the main sequence, with this very specific balance between energy production in the core, coming from nuclear fusion of hydrogen into deuterium and later helium, as in all the processes that we discussed last week. This energy eventually reaches the surface and escapes the surface, coming to us as we see it from our sun with all the light of day, and all the stars in the sky that we see as dots of light from this luminosity escaping from inside all the way to the surface and coming outside to us. So there's an energy balance between whatever energy is produced and whatever energy leaves the star. Although as we see, it's not an instantaneous process. It actually takes a long time for energy to come from the center all the way outside. And the star can maintain this equilibrium for as long as it has enough hydrogen and the proper conditions for burning hydrogen in its core. And next week, we'll talk about what happens when the hydrogen runs out. But there are still a few more topics we need to cover on the internal of a main sequence star, discussing how this energy dissipates from the inside to the outside, and how to complete a set of equations to determine the structure of the star. So we showed these plots again also last week, showing the different measurements or functions that we can analyze discussing the structure of a star. This is in particular is the standard solar model, so the model of our own sun, Sol. The easiest one, of course, to understand is mass. Here in solar radii, going from 0 to 1, of course, there's a 0 mass up to radius 0 from the center of the sun, but then the sun accumulates mass as it goes outside. And this bottom left plot is, of course, complementary to the right bottom plot, which says that the density is maximal at the center and decreases outwards, which means that the mass accumulates first very rapidly and then slowly levels off into the outer layers of the sun, which are much sparser, and the mass doesn't change so much towards the outside. The part where the density is very, very high is what we usually call the solar core. More accurately, we can relate the density also to temperature. The denser we push the gas, and the higher the pressure is, of course, through an ideal gas law, the temperature will be higher, which means the temperature is maximal at the center, as we said, approximately 15.7 million degrees Kelvin, which means nuclear burning can happen, and it decreases towards the outside. Decreases rather slowly until it levels off at the temperatures that we actually see near the surface, which, as we remember, is only something like 6,000 degrees Kelvin. So many orders of magnitude lower than the temperature in the core. What that means is that the conditions for nuclear burning do not persist throughout the sun, which means that the energy production or the luminosity mostly comes from the core. And that's represented here in the upper left plot, with the luminosity also growing in the core until it levels off, basically when the temperature and density decrease enough, low enough, that hydrogen burning can no longer be sustained. So of course, so just as the mass grows, the luminosity grows, but it only grows because the volume grows. The specific luminosity or the energy production per volume actually goes down as the temperature and density go down, until eventually we get to the end of the core of the sun, here marked at approximately 20% of the radius of the sun, when there's basically no more energy production. So from that point on, the energy escapes further and further outside to the surface and eventually to us, but no more energy is produced from nuclear burning outside of the core. So typically we can discuss the sun in at least these two generic, broad categories, talking about the core of a star, the sun or any other star, the core, which is the active part where energy is actually produced, and the rest of the star, the outer part of the star, outer to the core. It's actually internal to the star, and as we'll see later, internal to the part that we see, the photosphere. But most of the star is basically just gas conducting this heat outside, this luminosity, without generating anything new. And these four profiles will have to be related. Temperature, luminosity production, density, and mass will obviously have to be related to each other through various equations. An ideal gas law would be an obvious relation, but of course there will be more. Pressure is not marked on these in one of these four, but it's also an important function to trace. And the stellar structure equations, or the equations of the structure of a star, will be the equations relating these different plots or these different functions as a function of radius, or as we'll see, as a function of the mass itself. So we covered the first two of these equations last week, here in a radial coordinate, the mass and the pressure equations. The mass equation is basically just telling us that the mass grows as we look further and further outside, and so add more mass density. So this function rho, we basically integrate over a surface of radius r, so a surface area of 4 pi r squared. Assuming spherical symmetry, it's a simple multiplication, and we have the derivative or the growth function for the mass. The pressure, as we said, is determined directly by the equilibrium, or the hydrostatic equilibrium. That is, the pressure can only grow in exactly the right amount to counter gravity from the addition of mass. Every element of mass, if you will, or any layer of mass at radius r has to be exactly balanced between the gravity pulling it in, which is g times the mass up to radius r times the mass of the same element, has to exactly equal the difference in pressure between the pressure from below pushing up and the pressure from above pushing down. Obviously, as we said, the pressure is a decreasing function. Pressure is highest at the center of the star and decreases outwards. So dP to dr is negative. It's a negative gradient of pressure, which exactly balances this gravitational force acting inwards. That's hydrostatic equilibrium. And this is kind of the diagram we gave last week, showing exactly what I just said. An element of mass has to balance the gradient of pressure from below and from above with the gravity pulling it inwards. And under the assumption of spherical symmetry, the left and right pressures cancel out exactly. So it's really, under spherical symmetry, a one-dimensional problem. R is the only variable. Pressure is not so trivial. Pressure can come from different sources, gas pressure or radiation pressure. In a star like our sun, gas pressure is the only thing that's relevant because the temperature is not high enough to induce a high enough radiation pressure. But as you'll see in the tutorial, for stars of higher mass, the core temperature can actually rise a lot higher. And because radiation pressure goes like temperature to the 4th power, while gas pressure is only linear in temperature, eventually as the temperature goes up, radiation wins out. And so the most massive stars will actually be dominated by radiation pressure in their cores. Okay, so this explains again what we saw 2 slides ago. Okay, so we had two equations, hydrostatic equilibrium and mass accumulation, but we had 3 functions, m, p pressure, and rho density. So when we have 2 equations and 3 variables or 3 functions, we're obviously missing one equation to close the system. And the simplest, not necessarily physical, but simplest assumption we can often take for another equation is to directly relate rho and p. And that's what's called a polytropic equation or polytropic models. The poly comes from having many different options. Basically, we define a polytropic index n, which is related to an adiabatic index gamma. And we just assume a simple relation, which is inspired by an ideal gas law and would include an ideal gas law, but not limited only to that. We'll try to take temperature out of the equation and just assume some ratio or some power relation between rho and p, so between the density and the pressure. And you can think of any of these as your typical favorite thermodynamic systems, an ideal monoatomic non-relativistic gas, so just ions or atoms or even electrons floating around if they're at low enough temperature to be non-relativistic. The polytropic index will be 3/2, which makes the adiabatic index 5/3. So P will not be linear in rho, it will go like rho to the 5/3. You can relate that through the ideal gas law to the temperature, because P is also linear in the product of the density and temperature. And so you can find the relation between all these 3 functions. T is a function of rho, or T is a function of P, P is a function of rho, P is a function of T, rho is a function of T. All of these 3 variables will be given as simple polynomials or just power laws of each other. A different system, when the system becomes relativistic, this can either be very, very high temperature atoms or electrons, when they're hot enough that the typical energy per particle is on the order of the rest mass. So the velocities become relativistic, and you can kind of think of it as a relativistic gas. Or naturally, for particles which are inherently relativistic, like photons, which always travel at the speed of light. In that case, we have fewer degrees of freedom per particle because the velocity is no longer a degree of freedom, only the direction of the velocity is a degree of freedom. Photons are always constrained to move exactly at velocity c. And so we'd have a slightly higher polytropic index n equals 3, which makes the adiabatic index gamma slightly lower, 4/3. So these are kind of typical numbers. And this equation, this third equation, relating in the simplest case P and rho, can be used together with the other 2 equations relating M, P, and R and rho together to complete a set of 3 equations. 2 of them will be differential equations, dm, dr, and dp, dr. The third is an algebraic equation. That is, that there are no derivatives in this. P is just a function of rho directly, no derivatives. In that case, we can kind of realize that we have 2 differential equations, 2 first-order differential equations, and 1 algebraic one. We can combine them to find a single second-degree or second-order differential equation. And that's called the Lane-Emden equation given here below. You'll also see a more detailed derivation of it in the tutorial. But basically, we can replace the coordinate r, which has dimensions of length, with this xi, so which is non-dimensional, has no units. We can replace our pressure, mass, density, etc., basically with powers of the function theta, which is also dimensionless. The scaling is basically relative to some typical length of the system, which will be R0, and the maximal density, which will be ρ0, which is the density at the center. So we can now address or discuss different stars which have a similar distribution of mass, density, pressure, temperature, etc., just by scaling them all to these same dimensionless parameters and scaling the result with whichever star we have, whichever core density and typical length we have. This dimensionless function can be solved mathematically. In some cases, it can be solved analytically. When n is 0, 1, or 5, it can be solved analytically exactly. If not, it can be solved numerically, and you'll have, I think, a homework exercise about that. And we find this plot here on the right, which is the density or the distribution, for example, of mass density of the star in dimensionless units relative to or depending on the adiabatic index or the polytropic index. So here we have, for example, 6 curves. All of them start, of course, at a core density of 1, the maximum, because we normalized the maximum to be 1 at the center. And we see that they decrease in different speeds or in different profiles, if you want. But these will give us profiles of the density of the star that obey our 3 equations: the hydrostatic equilibrium, the mass accumulation, and the equation of state, the polytropic equation of state. So then if we measure a star, and we know, for example, the radius of the star and the mass of the star, we can try to start thinking which of these polytropic indices will be the best fit for that star, and kind of start inferring the internal structure and doing more complicated numerical operations or studies, assuming that the star has a polytropic profile. So it's a good analytic model that we can use. It's not very complicated. It basically depends on 3 numbers: the index, the core density, and a typical length scale. And with those 3 parameters, you can describe the full analytic profile of the star, if you're lucky and it works. And I'll tell you that it never does, but often enough, it can be a first order approximation or a first guess that you can use.
Can you repeat how you calculate the polytropic index, or you can't calculate it just?
If you know what the star is composed of exactly, you can try to compute the polytropic index. For example, if it's a ball of photons, then you know the polytropic index will be 3.
Okay.
If you know that the star is very cold, then you can assume that it's non-relativistic, it's just a gas, and then you can talk about whether it's monoatomic, diatomic, etc., and infer the polytropic index from that. The polytropic index, as you learn in thermodynamics, is related to the number of degrees of freedom per particle. So a monoatomic gas means just one atom has 3 degrees of freedom, can go in one of 3 directions in space. A molecule, for example, nitrogen 2, the most prominent gas in our own atmosphere, N2, has the 3 degrees of freedom of spatial directions, but it can also have an orientation and spin directions. Internal degrees of freedom, it can vibrate, it can oscillate. Many different things can happen if you have a composite molecule, and that will change the polytropic index. So this is good if you know exactly what your composition is, and you can calculate the polytropic index. And from that, you have a lot of information. You can do this for an atmosphere of a planet or a star, typically along some region where it doesn't change too much. If you have a gas, if you have a star, part of which is ionized and part of which is not ionized, you'll have different equations of state for both of these layers. And so one polytropic equation will not suffice for the entire star, which is why no star that we know is completely obeying a simple polytropic equation. But oftentimes it's a good place to start, and it can give you a lot of power when you do analytics, even if it's only about a part of the star and you want to stitch some of them together or kind of analyze the movement from one regime to another regime in the same star.
Okay, thank you.
Okay. Life, of course, is not that simple. So typically, we can't just assume a polytropic equation. Also, we left out a very important part of the star, which, of course, is energy production. As we said, what powers the star, what gives it temperature and thus pressure, which opposes gravity, is luminosity. And luminosity also kind of reminds us that the star is always losing energy. So it's never really in equilibrium. It can only be in semi-static equilibrium or in some stationary equilibrium. The star is always producing energy from mass and releasing energy in the form of electromagnetic radiation into the universe. So when we add this consideration, we have to look at where and how this energy is produced, first of all. And that is this equation, dl/dr, which tells us that the more we move from the center of the star outwards, the more energy is being produced internal to that surface, to that coordinate. This is basically a volume effect, right? Again, when r is 0, you're looking at a single point in space. A single point in space produces no energy. But when the radius grows, you're accumulating more and more matter, which is hot and is producing energy. And so L has to grow, which means dl/dr will always be positive. And how much will it grow by? Well, when you go to radius r, you'll add the surface 4 pi r squared times the density of matter at that radius, which is rho of r, assuming spherical symmetry, multiplied by this other function q, which is energy production per unit mass. And in general, it can be a very complicated function. It will depend on density, chemical composition, temperature, and all of those things that go into determining which nuclear processes are actually taking effect, as we discussed last week. And we might remember that some of the nuclear production processes are actually very strongly dependent on temperature, right? There's a T to the 4 power in the PP chain. There's a T to the 17 power in the CNO cycle, and the T to the 40 power in the triple alpha process. So this Q is actually hiding a lot of dependence indirectly on temperature and density and chemical composition and other things. But under the assumption of spherical symmetry, we can just put that all into a function of R, because all of these functions will themselves be functions of R. Okay, Q will typically be maximal at the center and decrease towards until it reaches basically 0 at the outer part of the star. As we saw, outside of the core, there's basically no energy production, but still the luminosity increases outwards. Or rather, luminosity production decreases, but total luminosity increases outwards. The last of the stellar structure equations, note that, of course, we added an equation, but we added a function. We added an equation, but we added L. So that didn't help us close off the system. We just added one equation and one variable. We need another equation. And that equation is the heat transfer equation, which might be considered one of the more complicated ones. It determines how this luminosity L of R, produced at up to a single radius, how it propagates basically outwards in the star. That is to say, what is the temperature gradient which causes heat to flow from the inside to the outside? You might recall from thermodynamics or from other daily experiences that heat typically flows from hot regions to cold regions, right? Heat almost never goes in the opposite direction. When there's a temperature gradient, the hot region will send off heat to the cold region. And so the temperature is what determines the direction of flow of heat and how much heat is moving around. Because we know how much heat has to move, basically the luminosity is telling us how much heat is exiting a surface. That's the definition of luminosity. It's an integral over the entire flux, or it's the flux over the entire surface. That tells us that there is a relation between this luminosity going out and the temperature gradient dT dr. And this gradient will depend on the mechanism which transfers heat, which in general can be one of many great types of energy conduction or heat conduction or heat transfer. There can be what we know in everyday life is heat conduction. That is, atoms get kinetic energy from heat. They move to areas where it is colder, and they take their kinetic energy with them. So that's basically heat conduction with particle elements. That's almost insignificant in a star. What's more typical in a star is radiation transfer. That is not massive particles which move from place to place, but photons which move from place to place. Because photon energy density goes like t to the 4, the derivative of that gives us this t to the 3, which appears here in the denominator. Another way to consider it, if you multiply by t to the 3 and a, remember the energy density is a t to the 3rd, you get on the left-hand side the derivative with respect to radius of t to the 4th. So basically this is telling us that the gradient of temperature is related to the gradient of radiation energy density, and that gradient is powered, or is what powers the luminosity exiting a surface. I see questions in the chat. Is the sun darker at the center or on the surface? What do you mean by darker? What do you mean by dark?
שהלומינסיטי קטן יותר.
So as we saw here, luminosity itself grows from the center outwards. That just means that there's more energy leaving a surface outside or at high R than the energy leaving a surface at low R. But you have to remember that the radius is larger out at higher R. R is obviously higher, and the surface goes like R squared. So there's more energy leaving a surface at radius R, but once you're outside the core, the brightness, which is, if you want to measure the actual flux, the luminosity, the energy or the power per unit area, will actually decrease, because eventually you reach an area which produces no more power. It only sends out whatever it received, but it sends it out over a smaller and smaller area. So it's a delicate consideration. The luminosity grows, but the flux can actually decrease. This only starts around where you stop producing energy, because in the core, the luminosity not only increases, the R doesn't only increase the surface area, it also increases the amount of enclosed volume and enclosed mass. And that mass is what produces this energy. So that's what the third equation was telling us, right? It tells us that the luminosity grows with addition of mass along a surface 4 pi r squared, multiplied by the energy production per unit mass, this function Q. So if you actually want to calculate the flux, what you'll be calculating is L divided by 4 pi r squared, and then you'll want to see how that changes with increasing or decreasing r. These functions are of course related, but not identical. Okay, the question of darkness is a little even more delicate because it has to do with what you can actually see from this energy produced, and we'll talk about that very shortly. Okay, so as we said, generally energy and heat can dissipate outwards in many channels, many different physical processes. The most common ones are radiation, convection, and conduction. In Hebrew, krina, hasa'a, and holacha. Conduction is almost irrelevant in stars, but radiation and convection typically are both important. The easier one to handle analytically is radiation. Convection is more difficult, and we'll talk about that at the end of today's class. Okay, so a recap, we have luminosity that describes heat leaving a certain surface up to radius r. This energy going out, this heat dissipation is driven by a temperature gradient. And if you want to, it determines the temperature gradient. Because it's radiation energy transfer, we have this t to the third in the denominator. That is the derivative of t to the 4, the radiation energy density. And we also have these two parameters here, kappa and rho. Rho is the same mass density. Kappa is something we'll talk about a lot. It's called the opacity. That is how easy it is for a photon, in this case radiation means photons, to actually take energy from one part of the star and transfer it someplace else in the star without being absorbed, scattered, or in any other way interrupted on its path. Opacity, in Hebrew, achirut, is what stops the photon from propagating or interrupts the propagation. And it's the reason that on a cloudy day, you can't see stars or see the sun, because there's some matter in between you and, for example, the sun, and the photons from the sun towards your eye have to go through this opaque object, a cloud, and they get dispersed and don't reach your eyes. Of course, if the cloud is very thin, if it's foggy, for example, you might be able to see a few meters, a few kilometers, or whatever typical distance before the photons are scattered. This exactly comes from calculations of the opacity kappa and the density of scatterers rho. And in the sun as well, if you want to dissipate heat, the luminosity L of R, through a temperature gradient dt dr, the density and opacity of the sun or the gas at that area are the governing factors behind this energy dissipation mechanism, this diffusion of this heat transfer. Okay, so this is now useful because this fourth function, dt dr, added another variable, but it didn't, and it added another equation. But we know we can relate this equation, this variable t, to P and rho through an ideal gas equation, if it's simple enough that we can describe the gas in those terms. And so finally, we have almost a closed set of equations. That is, we still have to discuss Q as a function of R, but we can assume we can do that because Q, the energy production, will also depend on rho and T. So if Q is a function of rho and T, that's not an additional variable. And the opacity kappa will also be a function of rho and T. So we're still not adding additional variables. More specifically, Q and kappa will be typically algebraic functions of T and rho. And there's an algebraic relation an ideal gas law between T, P, and Rho. So we have these four differential equations, ordinary differential equations, first order, one variable R under spherical symmetry, plus three algebraic equations. And the system is closed. There are enough equations to cover all the variables. Theoretically, if you can write these equations down, you can solve them. That's not easy, but it is at least doable. Any questions so far? I don't see anything in the chat. So we'll move on. Again, these are the four equations determining stellar structure, mass, pressure, luminosity, and temperature, given in terms of the radius r. Oftentimes, it's easier to write the equations in a slightly different form by replacing the variable r by the variable m. M is the mass variable, and it just tells us how much mass is given up to a certain radius, for example, a certain point in the star. The reason that's useful is because you can see many of these equations in terms of radius have this recurring factor 4 pi r squared rho, which is just, if you multiply by dr, just gives you the accumulation of an element of mass when you increase the radius by dr. So this first equation, dm, if I now multiply by dr, dm equals 4 pi r squared rho r dr, is basically a change of variable equation. You can think of it as what you learn in mathematical physics, switching the variable of integration or switching the variable by which you use to describe the system. So if we just flip dm dr to get dr dm, and that tells us that the radius grows with the growing mass parameter, and the rate of the radius growth is basically decreasing with 4 pi r squared, because the same mass is now distributed over a surface of 4 pi r squared. And rho, of course, the density of mass at that radius. So we can just switch, do a change of variables from r to m. Carrying through that change of variables, that is replacing every d to dr by d to dr to dm times dm, we find the Pdm is now a little simpler. There's no longer rho on the right-hand side. The reason there's no rho is because rho, as we see from the top equation, is part of the ratio of differentials. The change of variables, the Jacobian, if you want, of the transformation includes rho on the inside. So now the Pdm equation is a lot simpler. There's no rho involved anymore. It's a simple function of m. And another m comes in through the denominator, through r, but it's simpler than we had before. It's no longer m times rho, it's just m. An even greater simplification is in the third equation, because the luminosity before we had to explain was growing by 4 pi r squared rho, that is the amount of mass that you added, times q, the energy production per unit mass. But by switching the variable from r to m, all of that 4 pi r squared rho is exactly the Jacobian. It's exactly the transformation. So now we can say exactly, even if you want by definition, that the increase in luminosity by element of mass is precisely the energy production per element mass at that location, or at that mass coordinate. So the third equation is now a lot simpler. And in the fourth equation as well, if you recall, we had kappa rho before. Now this rho will just disappear as part of the Jacobian, and we'll have a function that's no longer dependent on rho, but it's indirectly dependent on rho because now we have the Tdm. The mass coordinate is what now determines the shape of our star. In many cases, it's easier to discuss a star using these equations, which is why many times you'll see that people don't talk about, for example, the core of the star being at radius such and such of the solar radius, but it being such and such percent of the mass of the star. The core is up to 10% of the mass, or 20% of the mass, or 30% of the mass. The mass itself can be used as a coordinate. And the relation, of course, between the mass and radius is given here. So we can see, in the case of our sun, for example, that if the luminosity stops at around a radius of 20% of the solar radius, the luminosity increase, that is, the core ends somewhere just over 20% of the radius, that corresponds to about maybe 40 or 50% of the mass of the sun. And that would be the core of our sun. The core where the energy is produced is only about 30 to 40% of the mass of the sun, and the rest of the mass of the sun is above the core, and it's basically not dense or hot enough to keep burning hydrogen into helium. Questions up to now? Okay. So now we'll start with a brief introduction to going deeper into heat transfer. And as we said, heat transfer can proceed by many different methods: conduction, convection, radiation, and different types of each of them. And they typically can all be present in parallel or together. Conduction is typically only relevant in relativistic white dwarfs or neutron stars, very, very dense stars. But otherwise, conduction is not relevant in stars, but radiation and convection are typically important. And flipping from one to the other will be also kind of an important feature in stars. Yes.
Can I actually have a question? Can I ask?
Yes, of course.
Are those equations considered like the Maxwell equations for stars? Like the main four equations?
They're the four structures, the four equations of stellar structure. They determine the structure of a star.
Mm-hmm.
If you want, in some courses in astrophysics, start with, here are the four equations determining the structure of a star. They're not really on the same footing as Maxwell's equations for multiple reasons. One is none of them are fundamental, right? They all include a lot of thermodynamics as well. They're also not exhaustive, right? They don't cover everything. For example, Q, that little factor which determines energy production per unit mass, or power per unit mass, is itself a function of a lot of nuclear physics going on behind the scenes. Which in the end, what we care about is temperature, pressure, and density, but Q includes and hides from us a lot of that. Kappa, the opacity, also hides a lot of physics and chemistry and other things that go into the different types of processes. And we're going into a short break soon, but basically the whole next hour we'll be discussing about Kappa and the different processes behind it. So the four equations of stellar structure are the main ones. They determine the macroscopic structure of a star from microscopic relations. But astrophysics is not an island of physics like Maxwell's equations, which in themselves constitute the entire field. In stellar analysis and astrophysics, it touches on everything, including, of course, Maxwell's equations, which we'll see in a moment.
Okay, thank you.
Okay, it's 1:45, so let's, before we delve into opacities and more complicated models, take a 15-minute break and reconvene at 1 o'clock.
Ofek?
Yeah. Welcome back. So heat transfer. Heat transfer, as we said already, is basically moving heat from one place in the star or one place in general to some other place, typically from someplace hot to someplace colder. And heat can't just disappear in one place and appear in another. Heat has to be carried by something, some heat carrier particle typically. And this is very, very similar to a model which you guys should all be familiar with from undergraduate school. I don't remember first year or something, or second, something like that. But basically in elementary E&M, electromagnetics, or basically even electric theory, you might be familiar with charge carriers in the form of Ohm's law, right? Ohm's law on the macroscopic level tells us that electric potential V or U is equal to R times I, Uri law, U equals Ri, or that that current is basically the potential divided by the resistance R, which is some property of the matter through which you want to have an electric current move or flow. Microscopically, that can be described with Kirchhoff's microscopic version of Ohm's law, which is that at every point, microscopically, you have some conductivity sigma. And if you apply an electric field E on that material or through that point in space with some matter with conductivity sigma, you'd get a current J. And in the simplest cases, sigma is just a scalar, just a number. So J and E are vectors and they're proportional to each other with some microscopic conductivity sigma. What does this conductivity actually consist of? Where does it come from? Why is gold or iron a better electric conductor than, say, air or wood? So Drude has a model of conductivity using electrons, basically saying that electrons are the charge carriers for an electric current. That is, they move electric charge from one place to another. The reason that electrons are very good at this is one, because they are typically very light of mass, so it's easy for them to get far away or to move fast from place to place. And two is, of course, that they have electric charge. And in fact, are the particle which has the most electric charge per mass. So they're very good at transporting that electric charge from one place to another. How do they do it? In the Drude model. In the Drude model, if you apply an electric field, here written as acting from the right to the left in the diagram on the right side, then that electric field will accelerate electrons because electrons feel a Lorentz force, which is equal to E times, so small e, the charge, times large E, the field. Charge times field equals force. That's basically the definition of an electric field. Because their charge is negative, they will develop a velocity or accelerate and develop a velocity going from left to right. So electrons will, if left on their own, feel this field and accelerate towards the right. They will not be able to do so for very far because whatever matter you're talking about, if it's a piece of wire, for example, other than just free electrons, also has a lot of atoms and ions, which are basically stationary in place. And they scatter these electrons because these ions themselves have charge. They can be positive, for example, but they'll deflect these electrons. So a typical electron will only propagate so far under the field before it hits some scatterer, some object which will scatter the electron and change its direction. And if you assume that it's completely, that it's random enough, then you can say that an electron hitting an ion will with some velocity will scatter in any random direction. And so on average, will go down from its previous velocity to velocity 0. But then will accelerate again under the same field, develop some velocity until it hits another scatterer, another ion which scatters it. Putting it together, Drude gave this model, which says that how do you then measure the conductivity or calculate the conductivity? Well, you have electrons. Each electron carries a charge E, its own charge, and you have a number density Ne, which is the number density of electrons. How many electrons per unit volume? So in a given unit volume, you have Ne times E as charge density, because that's the density of charge carriers times the charge per carrier, the electron charge E. This charge density, Ne, will move with some velocity. What is the velocity at which it will move? Well, velocity comes from the acceleration, which comes from the force. So the force is E times E, that's the Lorentz electric force, divided by the mass of the electron gives you the acceleration. That's just Newton's second law, A equals F over m. And so if the field is constant, then you can assume that this acceleration is constant. How long will it operate for? An average time, which we call T mean free path. That is the time during which the electron can move uninterrupted as a free particle until it hits something. And that gives you everything you need. It gives you charge density times acceleration times time is charge density times velocity, and charge density times velocity is exactly current density. So then Drude just picked out this E, the field, from the right-hand side and collected everything else in defining the conductivity. There's Ne, E comes twice, once from the charge carried, once from the charge feeding the force. So there's E squared, the mean free path of the free flight time divided by the mass of the charge carrier, Me. And this is a good model in many, many cases. It tells you who's carrying the charge, how much charge they carry, and how fast or how far they can carry it. Basically, the field E determines the velocity, divided, of course, by the mass, determines the acceleration, and the time between hits, successive hits, tells us basically what will be the drift velocity, Vd, which is the typical velocity an electron will reach until it hits something, gets scattered, effectively drops to velocity 0, and then gets reaccelerated again from one hit to the next. Has anyone not seen the Drude model before? Okay. Who has seen the Drude model before? I see one hand, 2 hands. 6 people have neither seen nor not seen the Drude model before. Okay, we're in a quantum superposition regarding the Drude model. Okay, this is the most simplistic version of the model, typically covered in elementary electromagnetism courses. Real life is more complicated because electrons are not entirely free in a solid, because electrons are not the only thing moving in a solid carrying charge. And to hear more about that, I recommend a course in solid state physics. But for our purposes, this is enough because we're going to use this analogy a lot when we talk about opacity of radiation transfer. And now we can start radiative transfer. So radiative transfer, again, we need to transfer not electric charge from place to place, but heat from place to place. Heat, that is energy. We need to move energy around. So something needs to carry this heat around. And typically it can be electrons, same as carriers of electric charge. It can be ions, which are typically not very good because they're at least 2,000 times heavier than an electron. So typically will move a lot slower. Full atoms, which unlike charge, you don't need to be electrically charged to carry heat. Anything can carry heat, so neutral atoms can do so as well. And these are grouped under the name conduction, or holacha in Hebrew, actual matter particles which have kinetic energy or heat in the form of kinetic energy, and they carry it around from place to place. As we said before, this is not very common in stars. Stars are very dense, and it's hard for matter particles to travel very far. So this is a very limited channel of heat conduction. Radiation conduction, more properly called radiative energy transfer, or krina in Hebrew, is when photons carry this heat. A photon obviously has energy, and it can travel very fast. It travels at the speed of light. It can take heat with it from place to place. The third option, also common in stars, is called convection, which is not just particles moving from place to place, but whole blobs of matter floating around from someplace hot to someplace cold. And we'll talk about this phenomenon next hour. The question that will determine which of these processes actually wins out or is most important in a star or in any system determines on the questions how much charge, or in this case, heat, can each particle carry, each channel can transfer from place to place, how fast they can move from place to place. That is the drift velocity we had before in the Drude model. And what's the mean free path time, or distance in time? How long in time one of these particles can move before it hits something and gets scattered, absorbed, or in other ways disappear, or distract from carrying his energy. And in terms of distance, how far it can get. What is the mean free path for our energy carriers or heat carriers? Okay, so not surprisingly, when discussing radiative transfer, photons are the thing that carries the energy. And as we said, a photon has energy proportional to its frequency n by Planck's constant. So the energy E of a photon gamma is h n. And the velocity, at least that is simple, the velocity is always c. If a photon exists, its velocity is c, the speed of light. At least in the approximations we're talking about, which is not considering the electric constants, but basically looking at individual hits of the photon or propagation of the photon between freely between successive hits. There are a lot of photons around, which is always important. When we talked about the Drude model, the number density n of electrons, Ne, was important in determining the conductivity, because you need charge carriers to carry charge, and you need heat carriers to carry heat. And luckily, there are a lot of photons available, because as we said, energy density goes like T to the fourth with this constant A, which is equal to 4 sigma over C. Sigma, I remind you, is the Stefan Boltzmann constant, which determines how much energy leaves a certain surface or a certain point, depending on its temperature. So the flux, or the power per unit area, power divided by area, is equal to sigma T to the fourth, and this is exactly the Stefan Boltzmann's law. It's determined by the temperature to the fourth power. Okay, or equivalently, you can think of it as the energy density at that point multiplied by c, the speed of light, the speed at which that energy density of photons will propagate, divided by 4, because you need to average over different directions, basically. Okay, so to remind you, we have the Stefan Boltzmann constant here, and its modification, the A constant, which you can kind of start guessing the orders of magnitude, about 10 to the minus 15 in units of joule per cubic meter per Kelvin to the minus 4 per Kelvin to the 4. That means if we're talking about temperatures of thousands of Kelvin, we'll have automatically something like 1,000 to the fourth power here, so about 10 to the 12. And we automatically see that we're going to have here energy densities in radiation photons alone. That's already in the order of joules per cubic meters. And that's a lot. Or, okay, already quite a lot, or approaching very high numbers, especially if we're talking about temperature in millions of Kelvin in the cores of stars, in which case we're going to have here something like 10 to the 24 and about 1 billion joules per cubic meter. So there's a lot of heat energy in photons, and so there are a lot of photons to distribute. So that's already a good candidate for carrying around energy. There's just so many of them and a lot of energy for them to carry. A more delicate question is how far each one of these photons can actually advance before it gets hit and dispersed by something. And here we have to be more delicate. So we define this L mean free path, the distance, the average distance between a photon is created and hits something which either absorbs or scatters it. In any case, modifies its direction. This mean free path L, of course, has units of meter. And the opacity is defined as 1 over L, or if you want, L is defined as 1 over alpha, the opacity. And note that different books and different people have different conventions. Some books will call this alpha with the letter chi. But it's easy to remember if you follow the units correctly. This alpha or chi opacity has units of 1 over meter because it's basically 1 over the mean free path. It tells you how long a photon will propagate before it stops propagating. What that means is, on average, that your luminosity will decrease with distance. If you have a single source of luminosity and you follow it through some distance, it will decrease by a factor E over a typical length of 1 over alpha. That is, if you consider the units correctly, you can say that the change in the luminosity over a distance r is proportional to L by a factor minus alpha. So it decreases by a factor alpha relative to what you had. Alternatively, the LDR will be minus L over the mean free path distance. It's very similar to radioactive decay, where we had a half-life in time, indicating that some quantity of matter or some isotope will deteriorate by half over some time period. In this case, we have a decrease by a factor of E over some distance, L mean free path. If alpha is constant, it's exactly the same as radioactive decay, because you can immediately solve this differential equation, dl dr over dr equals minus alpha L, to get exponential decay. L will then decay like an exponent of minus alpha r. Again, alpha is units of 1 over distance, so the exponent is dimensionless, or equivalently, decay exponentially like 1 minus r over L mean free path. After 1 L mean free path, you'll have 1 over E of the original quantity, the original luminosity. After 2 mean free paths, you'll have 1 over E squared of the original luminosity, etc., etc. So if this alpha is a big number, that means L mean free path is a very small number or small distance. And that means that your luminosity can actually decay quite fast. However, alpha is almost never a constant. It will depend on the local conditions. So it will typically be a function, and under spherical symmetry, it will be a function of just one dimension, our r, the radius, the distance from the center of the star, or in other cases, the distance from the edge of the star or into the atmosphere, or any other typical distance along which you want to follow the light rays propagating out, or the photons propagating out. So because alpha is changing, it's not easy to work with. Solving a differential equation when the right-hand side is not a constant factor, but something that's variable, is difficult. So the solution astronomers do to that is to define a new parameter, tau, which measures optical depth. And tau is defined in the following way. If alpha is a function of r, then define d tau to dr with the factor alpha. So just include the variability in your definition of distance if you want another change of variable, changing from the variable r to the variable tau. And the Jacobian, in this case, the transformation, is precisely this opacity. What that means is if you integrate both sides, you get tau as an integral of alpha r dr. And if you check the units, because alpha is 1 over distance and you integrate over distance, you get that tau is a dimensionless number. So the optical depth is now, in some sense, a measurement of depth, of distance, but it's in dimensionless units. So it's just a number. And that number is basically the number of hits a photon is expected to go through along a certain path. So at an optical depth of 1, or up to an optical depth of 1, the number of expected hits will be less than 1. At an optical depth of 100, that means you expect the particle to have gone through 100 successive hits during its path along that distance, which means the power will be e to the minus 100 and completely insignificant. Okay. Because tau is just a number and it's no longer dependent on anything, it's easier to write the differential equation, dl, in terms of d tau, the optical depth. And that's the simplest differential equation you could ever think of. dl equals minus L d tau, and the solution is immediate. L decays like the exponent of minus tau. The optical depth tells you how much of the luminosity, how many of the photons don't make it past that distance because they get scattered or absorbed or any other process, any other opacity process. Questions up to now? Okay. What then determines this opacity alpha? So we said it measures the typical distance before a photon hits something. What can it hit? Well, it can either be an absorber or a scatterer, but it will be some other particle or some other thing that can impact it. And so it will very, very easily be seen that similar to the Drude model where we had the electron density, in this case, we'll have the mass density, rho, because, and multiplied by some factor, which will be K. K will be the opacity per target, or per object you can hit, the photon can hit. So the per target radiative opacity. And the rho will be the mass density of those targets. What that means is, if you have a certain type of targets, say atoms or free electrons or anything like that, each of these elements will have a typical inherent property K, which tells us how likely it is to scatter a photon or to absorb a photon. And the more of them you have, the denser the medium is, the harder it will be for a photon to go through. Another way of thinking about it is that you can split this rho, mass density, into a product n, which is number density, times mass per target, the mass of the atom that absorbs the photon, for example. And then you can group this mass, which is a property of the particle that scatters the photon, times K, which is again an inherent property of the particle scattering the photon, and get this sigma, which is a property again just of that particle. And will tell you how many particles there are. or how many there are per unit volume, the density of those scatterers, of those targets. And sigma will be the per target inherent property, which tells you how likely that single target is to scatter or absorb a photon. And some of you might have already heard in a similar context, the name cross-section for this property sigma. Note this is not the same sigma as Stefan Boltzmann's constant. The units are different. This is just target area, simply in units of area, meter squared. Okay, and it tells you basically if a photon approaches a particle, how big that particle, or how big in some sense that particle appears to the photon, how much of the photon's possible trajectories will be blocked by that particle. In kind of a hard sphere analogy. Yes, Jonathan.
Sorry to interrupt. The calculation for the cross-section is the same for the calculation of cross-section we did in analytical mechanics in the second year.
In which mechanics?
Analytical mechanics.
Depending on which process you analyzed. If it was a particle-on-particle scattering, then it would be the same thing. Okay. I mean, if these were particles, you calculated a cross-section for photons on a particle, then it's exactly the same thing. Because we're talking here about cross-section for absorbing or scattering photons.
Okay, thank you.
Okay. So again, we have this alpha opacity in units of 1/meter, 1/length, basically how long before you hit a target, as a product of the density of targets and the size or area, effective area, the cross-section of a single target. And you can think of that with this diagram here below, with, for example, a photon coming from the left moving towards the right. There's some density of these balls. Each ball is given a radius or appropriate to the surface area or the effective cross-section it has towards the photon. And so the photon has to cross between all of these different possible targets without hitting any one of them. If you look at it from the photon's perspective, then what you see is basically each of those targets in front of you. And the ratio of the area that is blocked is exactly the number of these targets, which is the volume, d squared times dr, times n, the volume density of these scatterers. So that's the number of targets in front of you. Sigma is the area of each of them. So multiplied by sigma is the amount of area that's blocked. Divide by d squared, which is the total area you could take, basically gives you the density of scatterers out of the total area that you have available to you. So the effective probability, if you will, of hitting something. So it's basically just n times sigma, this same alpha, the number density of targets times the cross-section of each target. So this again is telling us a relation between alpha and this n and sigma, explains the relation, which tells us the relation between optical depth d tau and actual length dr. And that ratio is precisely n times sigma, the cross-section per target times the density of targets. And if you integrate over that, then again, you find the optical depth is really an integral of these microscopic properties, K, the opacity, times the mass density rho, or in terms of cross-sections, the number density times the cross-section per target. Okay, so this gives us a way to calculate tau or to calculate the opacity of some medium. If we know what's in it, we know the density and we know the effects involved. What cross-section each of these targets provides to a photon. Questions so far?
כן, זה בהנחה שהמצב הוא קבוע, כלומר שכל החלקיקים נמצאים במקום ולא זזים. אבל זה אמור להתפתח עם הזמן.
We don't have to assume that the particles are not moving. We just have to remember that typical matter particles will move quite slow right? They'll have kinetic energy, which is determined by the temperature. And you can calculate the typical velocities of a particle in a star, and then compare that to what you're trying to scatter, which are photons. Photons travel at the speed of light. So from a photon's perspective, these particles can be moving around, but from a photon's perspective, everything is stationary. Okay, so it's enough to assume that it doesn't change too much over the length of one mean free path or over the time it takes a photon between successive hits. But we'll see very shortly that that's a fair assumption because things typically move quite slow. Matter moves quite slow, and these photons actually move very fast. And we'll see that the time between hits is really, really short, unbelievably short, actually. So that's not we don't have to assume that. It's just a very good approximation that happens anyways when we're talking about the internals of a star. Okay, so I kept saying when I discussed opacities, absorption or scattering. Those are different types of processes, which for our models in this level are basically the same. They stop a photon traveling in one direction from continuing its travel in that direction, for example, outside of the star with increasing R. But when you want to actually calculate it, you need to do the microphysics of exactly which types of processes are relevant. And so you typically separate, one typically separates K, the opacity, in meters squared per kilograms into two types of processes, absorption processes, kappa, and scattering processes, sigma. Kappa will just say what is the chance of a photon hitting something, being absorbed, and you don't have it anymore. Sigma will be the opacity or the cross-section or the weighted cross-section, and times sigma for photon hitting and continuing with the same frequency, the same photon in some sense, but in a different direction. So there are slightly different types of processes. Also note that this is now the third sigma we've seen today, and it's also different. This sigma opacity has units of meters squared per kilogram, not cross-section, which had units of meters squared, not the Stefan Boltzmann constant, which had units of watts per meter squared per degree Kelvin to the fourth. So you always have to be kind of careful. Astrophysicists like to mix a lot of notations. Always check the units and check exactly what it is that you're calculating. A further complication, which we have so far ignored, is that all of these processes, scattering and absorption, are typically not independent of the type of photon we're discussing, the frequency of the photon. Many absorption processes will be only relevant to very specific frequencies. For example, who can think of absorption processes which are very specific to particular frequencies?
Absorption line.
Absorption lines, exactly. Chemical, atomic, molecular, quantum mechanical absorption lines. An atom with an electron which can hop between specific levels will only absorb at very specific frequencies with energies corresponding to the energy gaps between those levels. So that would be a kappa process, which looks like like a cone. It'll be basically flat, but it will have spikes at very specific frequencies of the spectrum. So that's a kappa, which will be very strongly dependent on frequency. And henceforth, K, the overall opacity, will be very strongly dependent on frequency. We can also have we then have to discuss different types of opacity processes happening in the same medium, separated in the simplest case by frequency. And then we have to say that we have to distinguish between processes operating on the same channel, which is the same carrier and the same frequency, or different channels, which can either be different carriers, like electron opacity or photon opacity, or the same carrier, but at different frequencies. So red and blue are different channels. They might have different opacity processes. And then combining and collecting all these different processes has to be done carefully for each of these types of combinations. And not surprisingly, maybe, if you have multiple sources of opacity relevant for the same channel and the same the same frequency, then to find the total opacity, you will add linearly all of the separate opacities, which also means that the highest opacity process will determine the overall opacity for that particular channel and frequency. This is completely analogous to connecting electric resistors one after the other, right? You have to add resistances. And the reason is the same, because if you add more targets for something to hit, it can hit them sooner. The total opacity grows. On the other hand, if you allow for multiple channels, the overall or equivalent opacity will be a harmonic sum. That is, 1 over the total opacity will be the sum of 1 over the individual opacities. And this, of course, is exactly analogous to connecting resistors in parallel. Because you have parallel channels, that means whenever you add another channel, you decrease the overall opacity or the overall resistance. You allow for another channel through which you can conduct or transfer charge, heat, or whatever. That also means that the governing opacity process will be the one with the least opacity. Just like in a parallel resistor system, it's the resistor with the least resistance which will effectively determine the properties of the system. The electrons, the charge carriers, or in this case, the photons, will just move in the easiest accessible route. That is the one with the least resistance, the one with the least opacity. What do I mean by channel? Is it a physically different channel? It is a physically different channel, but not in the sense of a different path. A different channel in this case will be, for example, red light and blue light. They'll both want to travel the same path from start to finish, but maybe there's an atom in between which only absorbs red light or only absorbs blue light. Then you can consider them as independent channels. And in that case, if it scatters more blue light, then the blue opacity will be higher, which means the overall opacity will be determined by the red opacity up until the point where only the red channel actually works. Red photons can propagate, and blue gets scattered in all directions and don't diffuse any heat towards the other side. And of course, we know an example of this, right? We discussed this in the first lecture. Who remembers the name of a process which scatters blue light more than red light? And what it's related to?
Rayleigh scattering.
Rayleigh scattering, exactly, Rayleigh scattering. The reason the sky is blue is because the molecules in our sky disperse more high frequencies than low frequencies. And so if you look deep into it, you scatter more blue. So the sun is actually, if you look at it directly, it's yellower than the rest of the sky. And if you look at it near the dawn or dusk, when it's lower on the horizon and the light has to travel through more atmosphere, and now we can say through a deeper optical depth, because the integral of the opacity of the sky will be taken over a longer distance from the sun to us through the atmosphere, through a longer patch of atmosphere, then optical depth is greater, it scatters more blue than red, and then you get a color change. So that's an example of different channels using the same carrier, photon, but at different frequencies. An entirely different channel is different carriers. For example, photons and electrons. This happens in solid state physics when you have electrons which can carry charge, holes which can carry charge, phonons which can carry heat and momentum. Electrons and holes can also carry heat. So in a solid state, for example, you have many different possible carriers for heat conductance and heat capacity. And then, of course, you'd have to calculate the opacity for each of them separately. Any more questions? Okay. So now let's do an example, an actual numerical example of how long it takes the photons, high energy gamma photons created in the core of a star in the nuclear processes we discussed last week to actually reach us, or as a start, to reach the edge of the star, to escape from the core and then escape the star and reach us outside. In vacuum of space, you can assume that the optical depth is close to 0. But what's the optical depth of a photon from the center of the sun all the way to the surface and to us? Okay, so first of all, we have to ask, what is the dominant process of opacity hindering that photon on its outwards journey? And in the sun and many ionized, highly ionized systems, that process will be Thomson scattering. Not an absorption process, a scattering process. It's scattering of photons bouncing off of free electrons. And you can think of this as a low energy limit when the electrons have low energy compared to their rest mass. That is low temperature relative to relativistic temperatures or energies, the low energy limit of Compton scattering. So Compton scattering is the exact correct calculation relativistically, but when the velocity of the electron or the energy of the electron is very low, you can basically treat the electron as almost stationary, and then the photon doesn't change color as it would in Compton scattering, because if the electron doesn't move, then the photon didn't transfer any momentum or energy. And so the photon will maintain the same energy, the same color, it will just bounce in some random direction. The cross-section for this process, the Thomson cross-section, sigma t, can be calculated in the limit of non-relativistic scatterings. And you find that it's this function of the electron mass and the electron charge, the speed of light, and it comes to about this 6.65 10 to the minus 29 meters squared. Again, cross-section is an area. This is the effective area a free electron presents to an incoming photon. It will scatter a photon if it effectively with this target area. And in this limit of low energy electrons, it's almost independent of the frequency. So it's a colorless feature. All photons will scatter off the same effective cross-section in this Thomson scattering limit. Okay, how many of these do we have in the core of the star? That is, what is the system and what's the density of these scatterers? So we recall that hydrogen is ionized at the Rydberg energy, 13.6 electron volts. That's basically ripping an electron from the innermost shell of hydrogen all the way out to energy 0, to the outside, 13.6 electron volts. If you convert that to Kelvin, it's about 150,000 Kelvin. Okay, 1 electron volt is about 11,000 Kelvin, so 13.6 electron volts is about 150,000 Kelvin, which is a lot, but still much, much, much lower, about 1% than the temperature in the core of the sun, for example, which was 15.7 million Kelvin. What this means is that basically all the hydrogen in the core of the sun is completely ionized. Okay, completely ionized. The ionization energy is 100th of the random energy any particle has in the center of the sun just due to its temperature. So effectively, you can put in a Boltzmann factor, but a Boltzmann factor of e to the minus 100 is virtually zilch. There's all the hydrogen is completely ionized and all the helium as well. Basically, the entire core of the sun is completely ionized. If then we consider that the mass fraction of the core of the sun is X mass fraction is hydrogen, and assume all the rest is helium, so Y, the helium fraction, will be 1 minus X, we can calculate the number densities of hydrogen atoms or ions and helium ions, right? So rho is the density at the core of the sun. The fraction of that density that is hydrogen is X times rho. And if you divide that by the mass of hydrogen, which is the mass of a proton, you get the number density, NH, number density of hydrogen atoms or protons in the core of the sun. Very similarly, NHE will be the number density of helium atoms at the core of the sun, just the same calculation, but with the fraction Y of helium and the mass of a helium atom. The mass of a helium atom is about 4 times the mass of a proton or a hydrogen atom, so we get a slightly different number, but the calculation follows in a similar fashion. How many electrons do we have per unit volume in the core of the sun? Ne, this number density of electron scatterers, free electrons. Well, each hydrogen atom, completely ionized, gives 1 electron, and each helium atom, fully ionized, gives 2 electrons. So it's just NH plus 2 and helium. And so if we add these two numbers together and do some algebra, we get 1 plus X rho divided by 2 mass of the proton. Okay, rho is the density at the core of the sun. We expect this to be a large number. MP is the mass of a proton. We know that to be a small number. And X is something that gives us some variability or some spiel, playing with either with different types of stars or different types of hydrogen to helium mass fractions. Alpha, as we said before, is the Thomson cross-section times this number density. And so we're going to calculate kappa, the opacity, as alpha divided by rho, or the alpha per unit, per density, mass density, which automatically gives us this sigma cross-section times 1 plus X over 2MP. And plugging in the numbers, this same sigma sigma Thomson, the cross-section of free electron scattering, 6 times 6.5, 10 to the minus 29 meters squared, times 1 plus X divided by the very, very small mass of a single proton, about 10 to the minus 27 kilograms. And we see that these numbers actually come out, cancel each other. 10 to the minus 29 divided by 10 to the minus 27, we get a factor of about 100. And in fact, that's what we get with the exact calculation, 0.02 times 1 plus X. There's a slight dependence on the mass fraction of hydrogen, meter squared per kilogram. This is the opacity at the core of the sun to photons propagating due to Thomson or free electron scattering. We can immediately convert this, this number, or calculate it more exactly in our sun, where we know that about 70% of the mass is hydrogen, maybe 71% or something like that. So we'll take an estimate of 0.7. And so 1 plus X is 1.7. And so we get about 0.034 meters squared per kilogram as the opacity of the center of our sun, the core of our sun, to photon scattering due to free electrons. And this is the highest cross-section or the highest opacity source in the center of the core of our sun. What then is the mean free path, or alpha? A typical density in the sun is about 100 grams per centimeter cubed. In the really core of the sun, it's about 150. Towards the outside, it goes to under 1. We can take an intermediate kind of order of magnitude value, take 100 grams per centimeter squared, a cubed order of magnitude, converted to meters and kilograms. This is about 100 metric tons per cubic meters. Okay? 100 times denser than water, than a ton per cubic meter. This is quite dense, right? Because then alpha, which is K times rho, will take our 0.034 meters squared per kilogram and multiply it by a factor of 10 to the 5. So we'll get 3,400, and the units here are meters squared divided by meter cubed. So 3,400 per meter. Again, this is alpha, the opacity, in units of 1 per meter, and it basically tells us how many hits a photon will undergo along some distance. And this is basically telling us that in a single meter, the average photon will go through 3,400 hits. Okay, inverting that, the mean free path for photon propagation in the core of the sun is about 0.3 millimeters. And if you divide by the speed of light, you get that the mean free path time, the flight time of a freely propagating photon in the core of the sun is 10 to the minus 12 seconds. So to Hodaya, who asked before if the system is changing or not, realize that the time scale over which this approximation has to hold is 10 to the minus 12 seconds. That's basically the time between a photon gets scattered and scattered again and scattered again. So the system, so if the star is basically stable and if the temperatures, which indicate the kinetic energy of the mass moving, are non-relativistic, you can completely neglect it and the photon will very, very quickly be scattered. The meaning of this is that a photon created in the center of the sun trying to propagate outside of the core, if the core has a radius of about 200,000 kilometers, which is about 20% or 30% of the radius of the sun, that's 10 to the 8, that's 2 times 10 to the 8 meters. In free path intervals, that's basically this number, this distance divided by L min free path, or multiplied by the number of hits per meter, you'll find that this photon will actually have to go through 10 to the 12 intervals on the way out before it can actually get outside. More accurately, it would have had to go through 10 to the 12 intervals on the way out if it were going in a straight line. But it's not going in a straight line because it gets scattered every 10 to the minus 12 seconds. Every 10 to the minus 12 seconds, it scatters into a completely random direction. So the actual path a photon follows is a random walk, Brownian motion, right? Mahalach shigo, a drunkard's procession. And as you might remember from thermodynamics or statistical mechanics, the growth of the distance from the origin in a random walk is not linear in time. It's a square root in time. Or in other words, the time it takes to travel some distance is actually squared in the number of steps. The number of steps is squared in the time and not linear. So approximately to do 10 to the 12 steps in the same direction to get away from the core, the photon would actually have to in order of 10 to the 24 steps in random directions until it can actually escape the core. And if each of these steps takes 10 to the minus 12 seconds, then the time it takes for a photon created in nuclear fusion in the core to actually escape the core is about 10 to the 12 seconds, 10 to the 24 times 10 to the minus 12, which is order of 100,000 or 1,000,000 years. Okay, that means the light that we see from the sun is not the photon that was created in the center of the sun. It doesn't just get to us. It has to go through billions and billions and billions of billions of scattering processes. It would take it, even if it were not absorbed or changed frequency along the way, it would take it about 1,000,000 years to come out. And of course, what actually happens is that during this time, the photon will get absorbed and reabsorbed and re-emitted. And so actually it will reach thermodynamic equilibrium through its process, and the actual photons that we see match a temperature profile at the outskirts of the sun, about 6,000 Kelvin, and we don't see the 16 million Kelvin photons created in the center of the sun, because they propagate toward us in the speed of light, but they get scattered so many times that they never actually make it out. Okay, I think this is a good time for a 15-minute break, and we'll continue at 2:10. I'm here for questions.
Can I ask a question then?
Yes.
Okay, I have I think a couple. First, what is the photons that are created in the skirts of the sun? What are they created from? Where do they come from? What is the process?
Lots of processes can create photons. Basically, every time you have temperature, you have kinetic energy, you have atoms bouncing each other, they will release some of the energy in the form of photons.
And that is not from the core. That is from the outside of the planet, like the
photosphere. It's what we call the photosphere, exactly because it's the sphere from which we see photons.
Oh, okay. That's the first question. Second,
and the temperature and their temperature profile will be determined by the photospheric conditions. So the temperature at the photosphere,
which is much lower than the core at temperature.
Yes, that's what we see, peaking around the green-yellow part of the spectrum, about 5,800 Kelvin.
Technically, we should get like once in a while a few core photons, no? Like really rare, but it should statistically it should reach us.
So under this approximation, we only consider a single opacity process, which was Thomson scattering. And we kind of understand the timeline it would take for a core photon to reach us if the only thing it were undergoing were Thomson scattering. But that same photon, of course, will undergo many other processes, and 1 million years is a long time. In 1 million years, it will probably, and we can calculate other types of processes, be absorbed by an atom, convey its kinetic energy to that atom. The atom will move other atoms. Eventually, one of them will re-emit a photon of lower energy. And so the energy there will be a downgrading of the energy per photon on the way out.
Okay, so basically almost impossible to reach us. And I also got a bit confused with the parameters. So I wanted the...
With what?
With the parameters.
Yes.
We talked about there is alpha.
Yes.
Is the general opacity?
Yes. It's called opacity, and it's in units of 1/meter.
And there is also K.
Yes.
Like, which is
K, radiative opacity in units of meter square per kilogram.
So K is what? It's like the opacity per mass, per area mass? No, per mass, I think.
You can think of it as cross-section per mass.
Okay, so K is, okay, so alpha is the opacity. We define it as opacity, and K is the cross-section per mass of the scattering piece and the absorbing piece.
Either. So K is total opacity, and it's composed of kappa and sigma. Kappa for absorption and sigma for scattering.
Okay, so alpha is the so what is, like, when do we use alpha? When do we use K?
So for example, alpha is immediately related to the mean free path, right? Alpha is 1/the mean free path, which means it's easier to relate alpha to tau, the optical depth. Tau is just the integral of alpha. It cannot, but alpha, what's alpha composed of? It's exactly K times rho, right? So it's the cross section per density, the cross section per mass, divided by the mass, multiplied by the mass density.
Okay.
So you can think basically of K as including all of the micro, the per target opacity.
Mm-hmm.
So it includes, it's K time, it's M times sigma, right? We had that, I think, before. K as M times, here. Yes, just as, I think I'm missing a parameter here. It takes the M part of out of rho. So it's, right, K would be, M and K together will give you sigma. So K will be sigma divided by M. So sigma is the cross section, which is why you have M squared, divided by M, which gives you the kilogram. So it takes all of the properties of the scatter, of the target. The cross section divided by the mass.
Only the what about the absorption though? Shouldn't alpha include the absorption as well?
Yeah, either scattering or absorption.
Oh,
Alpha includes both.
Okay.
But it gives the target. Kappa K includes the cross section of the target divided by the mass of the target. So everything that describes the target is in K.
Okay.
But then how many targets you have? How many targets do you have? Density rho.
Mm-hmm.
And together they give you alpha, which is the per point opacity.
Yes. I think the thing that confused me is that alpha equals n sigma, which leaves out kappa.
It's a different sigma.
Oh, this is what confused me because I know that alpha should include absorption and scattering, and here
yes. When you write alpha equals n sigma, mind the units, n is 1 over meter squared. It's number density per volume. Alpha is 1 over meter. So this sigma has units of meter squared, it's cross section. Okay. And it can be cross section of any process, scattering or absorption.
Okay, so it's a general cross section, not the scattering specific cross section.
Exactly.
Okay, that's it. That's what got me. Thank you.
Any more questions?
For me.
Okay, so I'll pause the recording and be back in 8 minutes. Okay, and we're back. So we discussed one example of how opacity can affect photons propagating in the sun. In this case, the effect of photons created in the core, not actually reaching us or taking a very, very long time to reach us on the outside due to an immense number of scattering processes happening along the way. A more interesting, maybe, phenomena is one that we can observe directly, or rather, one that we can't help but view directly, and that's called limb darkening. So I'm taking here the same two quadrants of the image we showed earlier, showing specifically the temperature gradient. So it's brightest, that is the highest temperature at the center of the sun, and the temperature slowly degrades outwards. It's not to scale in any sense, but kind of shows us how the temperature diminishes from the maximum in the center all the way to the outside. And now we have to ask, which photons do we see? Which photons reach our eyes and our detectors here on Earth? We said that they're not the photons created in the core, obviously. We just talked about that. But which do we see? Well, we also don't see just the photons created at the very edge. We can see slightly more into that. And how far into the sun can we see? Well, that's exactly what the parameter tau optical depth tells us, right? It tells us approximately how far into some medium photons can propagate outwards before they get scattered. Tau equals about 1 tells us this an optical depth equivalent to about 1 scattering of a photon on the way out. And if we want to take it a more exact number, we define the photosphere, that is the outer part of the sun from which we can see photons, to reach all the way to tau equals 2/3. Why 2/3? Because e to the minus 2/3 is about 50%. So that's basically the depth, the optical depth in the sun, where half the photons created there or out of there, further out from there will reach us, and 50% of the photons created there or more inwards will not reach us. So the profile of temperature, the photons that we see from the sun, can basically be assumed to be coming from this edge of the photosphere from about an optical depth of 2/3. So that's what defines the photosphere, tau at 2/3. But that's not the end of the story, because this 2/3 of optical depth depends on which direction you look into the sun. If you're on the right side of the sun here, and you're looking at a photon created from point A at a certain length L from the surface, then you see that because this distance L penetrates directly in the radial direction, it will reach point A at a very high temperature, here marked in yellow. If, on the other hand, you're looking off center from the sun, someone to the right of point B, the same distance L will not be directly directed radially towards the center. It will be kind of scathing part of the sun. So this optical depth, the same optical depth, 2/3, will terminate at a lower temperature that is closer to the surface in temperature-wise or depth-wise. That means if you're looking at point A, you'll see a high temperature. If you're looking at point B, you'll see a lower temperature. We recall that luminosity from surface area, the Stefan Boltzmann law, tells us the temperature goes like T to the 4th. So even this maybe small difference from A to B in terms of temperature will actually have a big impact on the luminosity, which is why if you manage to look at the sun with some filter that blocks out too much shining and really reduces it down to something you can bear with your eyes, you'll see this effect of darkening towards the edges. The center will be much brighter than the edge. Near the edge, that is when you're looking close to the end of the photosphere and you're seeing deeper into or further into the cold parts. For a purely geometrical consideration, the edges will actually look darker and will rapidly drop to black. Okay, this has historically been an important process. One reason is that if you try to measure things about the sun, for example, by a transit of a planet like Mercury or Venus, an inner planet, seeing them as a dark spot, it's actually quite difficult to tell when that planet enters in front of the sun, because the sun itself becomes black at the end, or turns dark. The limb is darker than the center, so it's not such an easy or accurate process. Today, of course, we can use this in many other ways. If the sun is no longer at a brightness or fixed temperature, we can infer things, at least about the temperature gradient or the temperature distribution near the surface in the photosphere, by considering the difference between a path ending at B and the path ending at A. And we can calculate the different colors coming from different directions of the sun and kind of understand a little more about what happens on the inside. Obviously not deep inside, but limited to about an optical depth of 1 from the surface. That is the photosphere. Yehu will give you a more detailed exercise about this process in the tutorial. Just notice that this opacity thing is actually something that can directly affect observations that we can actually do, and sometimes for better and sometimes for worse. Okay. We mentioned earlier that radiative processes, radiative transfer, can actually have a very strong dependence on color and frequency, that this sigma t to the 4th is averaged over all frequencies, but really you have to to calculate all types. This third line here is an error. I'll delete that from the notes later. But the fourth line is important, and that is we can have many, many different types of processes involving photons scattering or absorbed by not just free electrons, that was Thomson scattering, which we covered, but by electrons and ions, and systems of electrons and ions. And these can involve free processes, that is a photon approaching a system of an electron around an atom, but free from the atom, and it remains free. Bound, that's the classical photon hitting an atom and moving a bound electron to a different energy level. So it's still bound. Bound free, which is ionizing an atom, or free bound, which is a photon hitting an electron around an atom, and then product being that the electron is now bound by the atom. And the photon gets scattered or something like that. And these are just the simple processes involving a single atom and a single electron. As you can see here on the right, a partial example list of many of these processes. For example, the top one, this is a bound-bound transition. A photon hits an atom, the electron jumps to a higher shell. The electron eventually jumps down to the original shell, releasing a photon. So this is a scattering process. The photon eventually gets scattered. The fifth line, E, we can see a photon hitting an atom, causing an electron to jump up 2 energy levels, and then drop down one by one, releasing 2 photons of different energies. In this case, we have a series of bound-bound transitions, causing the energy of the photon, the incoming photon, to be distributed between 2 exiting photons. So it's not just scattering and not just absorption, but this is actually a nonlinear process. We have exiting photons in different frequencies than those that came in. That is, the energy was divided between 2 distinct photons on the way out. And many, many more processes which can depend on frequency and thus complicate the situation. We mentioned Rayleigh scattering before. So Rayleigh scattering comes from dipole interactions between incoming radiation photons and anything capable of developing a dipole moment. Water molecules, for example, have a very strong dipole moment, so they will be very strong scatterers of Rayleigh processes. And to put it in quantifiable terms and not just in words, the cross-section, sigma, for Rayleigh scattering, we can see is strongly dependent on the wavelength, lambda to the 4th power in the denominator, or equivalently, the frequency ni to the 4th power in the numerator. That is, high frequencies have a much stronger cross-section for Rayleigh scattering. That is, blue will scatter a lot more. And as we already discussed, that's why the sky is blue. This frequency-independent Rayleigh scattering cross-section.
אופק?
כן, yes.
אתה יכול לחזור לשקופית הקודמת? מה זה החצים, נגיד, ב-D ו-G?
In this diagram, taken from a book here you can find in the library, the squiggly lines are marking photons. The wiggles mark photons coming in or out, and the straight lines mark electrons. So process C here is actually an emission process. It's an electron hitting an atom, scattering itself off of the atom, causing an electron to increase in, to jump up energy level. Eventually that electron will drop down to the original shell, causing a photon to be emitted. So this is not just absorption or scattering, this is also an emission process. And you can consider that as another way that photons and electrons kind of change energy between atoms and electrons and photons, and on their way out, of course, photons and electrons will go through many of these processes, and this is what contributes eventually to the thermal equilibrium. That is, that we almost don't see photons coming from the core, because eventually they'll either be dividing up their energy, as we see here in process E, between multiple photons of lower energies, or as we see in process F, giving up some of their energy to atoms, and through the atoms to electrons, and transferring it to kinetic or thermal energy. So all the energy produced in the center of the sun, even if it is produced as radiation and photon energies of high energy photons, by the time they reach the surface, it will have converted through many of these processes to just random thermal energy, kinetic energy, thermal energy of either the atoms, the ions, the electrons, or the radiation, but the radiation near the surface. So lower temperature, about 6,000 Kelvin, which is what we see from the photosphere, and not the 16 million kelvins at the core of the sun. Some places give full courses on radiation transfer and radiation processes in stars. Even this list is only the beginning of possible processes which can happen. Okay. Another important example of a color-dependent process is an absorption process called bound-free. That is basically ionization. An atom which has an electron bound to it absorbs a high-energy photon, causing the release of an electron, and the surplus energy goes into kinetic energy. So this is an absorption process. That is, the photon is completely absorbed, not scattered. And the two interesting things we can tell about it. One is that, of course, there's a minimum energy threshold for an atom to be able to absorb a photon and ionize. That is the ionization energy. For example, we see for the hydrogen curve here in black, it starts, not surprisingly, at 13.6 electron volts. A photon with less energy than 13.6 electron volts will have zero cross-section for a bound-free absorption process, because it cannot ionize the atom. It cannot cause a bound electron to go free. For helium, we know we have about 4 times as high ionization energy, because Z equals 2 and not just 1. And so we see that this sharp onset of the process is higher up. And again, we have neon, oxygen, helium plus ion. Sorry, helium plus ion is the one that's 4 times. Helium itself is a little less, because you have 2 electrons and you just need to ionize one of them. That's neutral helium. But basically you see this typical feature, which is nothing until the ionization energy, and then a large jump in cross-section to the actual, the maximal cross-section for ionization if you get a photon with exactly the right energy. And then a typical decrease, which goes like the frequency to the -3, or goes like lambda to the 3rd. So it's not just a delta function or a jump function. It's a jump and then a power law decrease, which is also color dependent. Notice this is exactly the opposite color dependence of Rayleigh scattering, because this cross-section goes up with wavelength, down with frequency. Rayleigh scattering went down with wavelength and up with frequency. So in general, in different regimes, many different processes will contribute and be relevant for calculating opacities. And because opacity is so strongly energy dependent or frequency dependent, it's very hard to work with. And so people often define some sort of average. It's called the Rosseland mean opacity. Again, we can consider different colors as being different channels. So those opacities will be added as in parallel, like parallel resistors. So there will be a harmonic average. And this is exactly what defines the Rosseland mean opacity. It's a harmonic average that is 1 over kappa of the sum, or in this case, because its frequency is a continuous variable, it's an integral from 0 frequency to infinite frequency, integral over the frequency ni, of 1 over the per frequency opacity kappa ni, with a weighting factor dBV dt, B ni dt, B ni, you might recall from lecture 2 or 3, is the Planck function, which tells us how much energy there is at a given temperature at every frequency. And it goes like ni to the third power times the Planck, divided by the Planck ratio 1, e to the minus k Boltzmann t divided by e minus 1 or something like that. The black body spectrum, basically. P is the black body function. So what this tells us is you have to, don't just add all the opacities for different frequencies on an equal footing, weight each opacity by how many photons are actually moving along in that particular frequency. And that's what gives us this, this black body Planck factor in here. The denominator is just a normalization. Because this integral is over infinite frequencies, to normalize it to 1, you just divide by the full integral without the opacities. That also works out the units. The units are just 1 over opacity on the left and 1 over opacity on the right, because all the integral and the B functions cancel out. So again, how do you calculate this? You have to calculate at a given temperature the Planck function and all of the opacities at every possible frequency, integrate over them, divide by the full integral, average out, and you get something like this surface function depicted on the right. Of course, it depends on chemical composition, because the different composition of hydrogen, helium, and metals will determine absorption lines and ionization lines, and all of these different per frequency and per molecule, per atom, per element opacities. And so you see that it's dependent, given here as an example for mass hydrogen fraction of 0.7, helium 0.29, and 1% of everything else. That's what we call Z, metals, everything above helium. One of the axes here is temperature on a logarithmic scale. The other axis is R, which is a proxy for density. It's basically density normalized by the temperature cubed, because what we're talking about always, of course, is radiation density, which is T to the 4. So there's some normalization here to get this on reasonable footings. And on the independent axis, the Z axis, the vertical axis, we have the log of kappa, the Rosland mean opacity. And as you can see, these functions are not simple. They have to, as you change the temperature, you change the averaging process, you change the ionization levels, you change which is more prominent. When you change the density, you change different types of opacities in a different manner. And so all of these things, when you actually want to calculate the atmosphere or the interior of a star, all of these processes become relevant and difficult. But just so you know, that's how you want to calculate an average, the Rosland mean opacity. Overall, we have a simplification of the temperature dependence. So here we have just one axis, ignoring the density. We have log of kappa, so the opacity on the vertical axis, and typical temperatures on the horizontal axis. And here we see that it goes basically from about 10,000 degrees, so just above the temperature at the photosphere of the sun, which is 6,000 degrees, and all the way to 100 million degrees, so all the way into the core. And as we said, in the core, Thomson scattering or electron scattering is the most important feature. In most of the interior, you'll find an opacity law called Kramer's law, which Yehu will show you and also give you the homework exercise to derive the opacity dependence on temperature from the relevant processes, basically free electron, free scatterings around ions in the star. And in very, very low temperatures, relevant slightly in the sun and more in M-type stars, colder than the sun in their photosphere, we have H minus opacity, that is opacity coming from lines of ionization of the H minus ion, that's one proton, hydrogen core, nucleus, with 2 electrons. So it's a negative ion of hydrogen. And it also has its characteristic lines and opacity traits. Okay, so that was an overview of opacity. And that brings us to the last item for today, the other type of heat transfer in a star. We said conduction was irrelevant in stars mostly, and we talked for an hour and a half about radiation transfer, but convection is another type of relevant process in stars. And convection is, like I said earlier, the bulk motion of blobs of matter, hot matter from hot regions to cold regions. And you know this process from everyday life. You know it from sitting in a room with heating, and you know that hot air rises and cold air sinks. And that's why when you want to heat a room, you have to consider things like where to put your heater. If you put it too high, hot air will go up, and you need to kind of balance those things up, balance those things out. If you have an oven and you want to cook, you need to balance where exactly the hot air flows. And if you've ever seen a lava lamp, this device, which was very popular when I was a child, of course, the lamp heats, provides heat to the liquid at the bottom, which causes it to get hotter, to increase in pressure, decrease in density, and then float up and create all of these bulk motions of blobs of matter held together by surface tension to rise up, cool as they rise up, and then drop back down when they're colder. So you have this interplay, this constant mixing motion of matter going up and coming down. So that's basically what I said. Another example, which you all know, is if you boil water in a kettle, when it gets hot enough, the bubbles of hot water created near the bottom will rise to the top and sometimes even reach the surface, and water vapor can come out of it. Again, and you have a bubbling or a boiling effect, which you see when you provide heat to one side of a container, that is the bottom of the kettle sitting on the hot plate, causing hot matter to rise. And you know that, and you know it's not always the most well-organized process, because there's a lot of randomness going around. This is very, very efficient if it's possible to do this, because you're not just transferring small particles carrying a little heat individually, you're just sending bolts of hot matter up into the atmosphere or up away from the core of the star. So this conveys a lot of heat. If it's possible, it will take over. And there's a slight side effect that you're not only transferring heat, you're also mixing up the matter as you do it, which is why boiling a soup mixes up everything in between. Matter actually moves very, very far from place to place as an inherent part of this convection process. It's matter moving. So now we have a short clip. You can find the link on YouTube. I also put it on the Moodle. This is an example of heating the bottom of a container. And if the fluid doesn't move, you just get layers of different temperature, a gradient moving up. If you allow the fluid itself to move, then as the hotter matter moves up, it of course also folds the shape. Again, if the matter doesn't move, you'll only get a gradient, just diffusion of heat. Nice, simple gradient of temperature. If you allow the matter to move, it itself will rise, and you have curvature and instant hydrodynamic instability setting in, bringing in the matter and kind of creating these folding effects with columns of hot fluid going up and cold fluid going down. This is very similar to weather systems, where hot air and hot water vapor goes up eventually cools down, and if it cools down enough, it turns back into water and falls on us as water droplets and rain. This is an example with even more changing a hydrodynamic parameter, which makes this an even more prominent motion, random motion, unstable motion, and even turbulent motion of hot matter rising up, taking heat with itself, going up, cooling off, and then coming back down. So this is a very efficient way of both transferring heat and matter. This is convection. Okay. Convection is not always possible, which brings us to the question of when and what is the condition allowing for convection. We saw that convection destabilizes because it moves bolts of matter around. It creates an instability, and so the criterion for convection is really a criterion of stability. So it's called the Schwarzschild criterion, after the famous astrophysicist that died about 105 years ago, Carl Schwarzschild. We'll talk about him more when we get to general relativity. And he described the situation as the following. We have two systems here, the left and the right. Both of them have a temperature gradient, here represented by a color spectrum, purple being very hot, blue being colder, then green, yellow, orange, and red. Obviously, the left has a steeper gradient, stronger change in temperature as you go up in the star or in the atmosphere. The right side has a milder gradient. The temperature doesn't change by so much. With high temperature also comes high pressure and high density, which is typically why the denser part is at the bottom. Gravity applies to mass, so it brings the denser parts to the bottom. What happens then if a bubble of hot matter from the purple region somehow manages to get dislodged and float up into a colder region? If it's adiabatic, you can assume that the temperature isn't changing, so the temperature remains this T1, this hot temperature. However, the pressure on the outside, P2, is lower than the pressure P1 at the bottom because the environment is colder, and so the pressure is lower. If there's less pressure on the outside than on the inside, that means the bubble will expand. The high pressure will cause it to expand, which means the density will decrease. So now you have this chimera bubble, this Frankenstein bubble, which maintains the temperature from down below, the hot temperature from down below, but a density which is less than the density down below. Not necessarily the ambient surrounding density rho 2, but some other lower density rho 3, lower than rho 1. Now, if this change happens is very, very prominent, then you can imagine that rho 3 isn't sufficient, that doesn't decrease fast enough. So rho 3 will still be denser than rho 2. If rho 3 is still denser than rho 2, then this bubble is heavier than its environment, which means gravity will pull it down. Right? Denser things sink, and lighter things, less dense things float. So if a bubble tries to escape the high density, high temperature region to a low density, low temperature region, but the density rho 3 remains higher, that is, it's still higher than rho 2, gravity will push it back down, and so the column will be stable against convection. Right? You can't actually expect this bubble to travel very far because gravity will pull it back down. However, if the change is very, very steep in the surrounding area, the surrounding region, rho 3 can actually decrease because of the pressure difference. Rho 3 will decrease so much that it will be less dense than rho 2. You can think of that as example as your bubble boiling in a kettle where the bubble is basically vapor and of course much, much less dense than the surrounding water. In that case, the bubble, which is very, very light, will actually be assisted by gravity. It will jump up. It will float up and escape. And that's when you're unstable. That's when you get convection. Because these hot bubbles are also very light, lighter than the surrounding area on top of them. And so the cold material is denser and will sink, and the light bubbles will jump up, up and escape. And that's the Schwarzschild condition for convection. So what it has to consider then is compare the gradient of temperature, how much the temperature changes, with how much the pressure changes, and see which one of those processes wins out in the environment. So Schwarzschild defines this delta function, which is the gradient, the temperature gradient. It's a dimensionless number. It's the ratio of the gradient of the temperature, or the logarithm of the temperature, to the gradient of the logarithm of pressure. And because it's a logarithmic gradient, it's dimensionless. And it gives us a number. And this number you can compare in the star, the given gradient in the star, to the adiabatic gradient. That is, how would this gas naturally behave given by its adiabatic index, which we discussed 2 hours ago, this gamma polytropic or adiabatic index. If the star's temperature gradient is stronger, that is, if the star changes temperature very, very fast, if there's a strong temperature gradient, it will overcome the environment and you'll get instability and you'll get convection. If the gradient of the star is lower than the adiabatic temperature gradient, then you're in the right-hand case. The gradient is not strong enough and there's stability. The bubble will sink back down. So this is kind of the Schwarzschild condition in terms of thermodynamics. What it means for us, I'll get to this in a moment. What it means for us typically is that we can compare this to what actually creates the temperature gradient in a star, which is the luminosity, or the maximal possible luminosity a star can maintain. And that luminosity, again, is related to the adiabatic index and to the opacity. So what we have to do is compare the luminosity of the star to the maximal possible luminosity one can maintain at the given opacity and adiabatic index. If the luminosity is greater than this number, then you'll have convection, because you're trying to get the temperature gradient. There's so much luminosity to get rid of. Basically, you can't just do it with radiation transfer. You're forcing a convection to form. If the luminosity is low, it won't happen, and you'll have stability against convection, and that region of the star will be mostly stable, and radiation transfer will do most of the energy transfer in that star. In observational terms, or in stellar terms, we try to understand where these two different regimes will take place in stars. And what we've come up with is actually that all stars have convection. It's always important. The question is where? So very, very small stars, typically less than about half a solar mass, so they're pictured here in red as kind of M-type stars, redder than our sun, are fully convective. They're convective all the way from the core to the photosphere. The entire star is one convection region, which means matter and heat gets mixed up all the time. Slightly more massive stars around the mass of our sun, from about 1/2 to 1.5 solar masses, actually have two distinct regions. They are radiation transfer dominated in the core. So our previous calculation about radiation transfer and photons is actually the governing process in the core of the sun. But outside of the core, when opacity changes and temperature changes, you actually start reaching convection. And this convection goes all the way to the surface. So the core is non-convective, but the outer areas, regions are convective. And this is related to what we said last week, that the sun doesn't perfectly mix its core. Not all the hydrogen will reach the core. That's because the sun is very good at mixing the material on the outside in the convective region, but the core is non-convective, so it doesn't mix. Mostly matter that's outside the core will never get into the core. So when the core runs out of hydrogen, the sun is basically dying. Above 1.5 solar masses, the situation flips entirely. In hotter stars, here depicted in blue, upper on the HR diagram, bluer and hotter, it's actually the photosphere and the outer parts that are radiative transfer dominated, and the core is convective. So these will actually mix the core quite well and keep mixing and keep mixing and keep mixing, but not really with matter from the outside, but just from recycling matter in the core. So even though the evolution of stars, which depends on how much and what types of fuel are in the core, and the chemical composition of the core, these things will be determined by convection processes, whether there is or isn't convection. Here on the right, you can see kind of another depiction of the same end result, which is depending on the mass of the star on the x-axis, which regions of the star are convective or radiative. And here you can see the y-axis is not given in terms of radius r, but in that mass parameter we discussed earlier, fractional mass m over m. And so you can see that our sun is exactly here at 0, log 0, 1 solar mass. You can see it's radiative for most of the star until about a mass of maybe 85 or 90% of the mass, and then the outside is convective. While heavier stars will be convective on the inside and then radiative on the outside, while small stars are going to be basically fully convective. We can see this, and this will be the last slide for today. If we look at the sun at a high resolution, and we can see this granularity, we can see these bubbles on the surface of the sun. Here we can see them from the size of Texas to about the size of Manhattan as the pixel size from this solar telescope. And these bubbles, apparent bubbles on the face of the sun, are exactly what you'd think they are. They are bubbles. They're convective cells. They're cells created by convection near the surface of the sun. And if we watch that in this clip here, we can see that through time, the solar surface is actually seen to bubble in this sense, to boil. We have convection, which mixes matter, moves it around. And if you follow this, you can actually see that the surface of the sun is not stationary. These huge convection cells, in the size of countries, constantly move and mix material and bring heat from down below up to the surface. And then the colder material drops back down below. And this mixing of the solar surface is, of course, a very active region of study because we can see it and because it can actually have effects on the Earth. Okay, that's it for today. Any questions? Completely shocked. Okay, I know we covered a lot today in stellar structure and maybe things that are less trivial, less familiar from other fields. So a little hydrodynamics, hydrostatics, a little energy transfer, radiative transfer, conduction, convection. I hope at least the radiative part is kind of familiar to you from electrostatics or from the Dode model in solid state physics or in electricity. But now, of course, I'm available for questions. You'll have a tutorial soon. And any questions about the homeworks, I'm here on email, on the Moodle forum, and of course, reception hours Thursday morning. Also, it's the middle of the Hebrew month or the Chinese month or the lunar month, middle of Ramadan as well, which means there's a full moon, and the moon is actually very close this month. It's a super moon, so you're welcome to go out and see it and have fun. I'm shutting off the recording.
Thank you.
Thank you.